What's up, y'all? Good to see you. This is section 5.3, Proving Polynomial Identities. And we did this back in chapter 3 when it was just x squared, but now we're going to show what it looks like when it's x cubed. Remember, an identity is an equation that is true for all values of x. An identity is, here's an identity right here. We got x cubed minus 8 is equal to all of this. And the question is asking you to show that all values of x are actually solutions. Not just one solution, not just two solutions or three, but every single real number and every complex number is also a solution. And I'll show you how we're going to do that. We're going to do it three different ways for this first one, and then just algebraically for the rest. So, as you can see here, what I'm doing is I'm removing these parentheses. I'm just going to algebraically manipulate this right-hand side so that it looks like this left-hand side. I'm going to do that by foiling. And you can see x is right here, and minus 2 is right here. It turns into negative 2. And then x squared is here, and 2x plus 4. Let's box method this thing. Let's multiply it all up. And you can see x times x squared is x cubed. Negative 2 times x squared is negative 2x squared. Negative 2 times 2x is negative 4x. Negative 2 times 4 is negative 8. And then you can see all the other terms are right here as well. Anyway, the x squared terms actually cancel, and the x terms, the linear terms here, cancel. And if the quadratics and the linear terms cancel, we're just left with x cubed minus 8. Those are the ones that don't have any like terms to combine with. And so then we're left with x cubed here and minus 8, or right here. And so therefore, algebraically, we made the left side look like the right side. It's kind of interesting because you could do this numerically as well. If you wanted to, you could look at this and say f of x is equal to, like, you could take this and take this identity, and you could make the left side equal to your first function and the right side equal to your second function. So x cubed minus 8, first function. X minus 2 times x squared plus 2x plus 4 is going to be the second function. And you can actually choose, like, if we're trying to find out whether or not all values of x work, let's plug a few in and see what happens. If you choose, say, for example, positive 2, and you put it into here, what do you get as an output? You get 0. Positive 2, what do you get as an output? You get 0. So it looks like 2 is a solution to this equation, to the original equation at least, because the left side equals the right side. It's a solution. 2 is a solution. Yay, we found one solution. But wait, if we plug in 1, we get negative 7 on the left side. We get negative 7 on the right side. So the value of 1 is also a solution. Turns out, it doesn't matter what values we choose for the x, we are going to get a whole bunch. They're all going to be solutions. So we're going to get a whole bunch of solutions. It doesn't matter what value of x you choose. The left side is always going to equal the right side. And that's represented graphically here. I've actually graphed x equals 2, 1, 0, negative 1, negative 2. They're all right here, all these 5 different x values. And the graph is actually, what it's doing is we're showing the left side and the right side, and they coincide. They're like two different graphs smack right on top of each other. It doesn't matter what your input is, your output is always going to be the same, left side and right side. I've graphed the left side here, I've graphed the right side here, and they happen to be the same. So that's graphically evidence that they're actually identities. Often the easiest thing to do is just going to be, if you're good with your algebra, then the easiest thing is not going to be to graph it or make a table out of it, but just to do a trick of algebra here or there. Or sometimes you're not even going to be able to graph them. Like, what if it's an imaginary, there's the letter I in here somewhere, then all of a sudden you can't graph it at all. So we've got to be able to do it algebraically. So let's prove each statement algebraically. Do this algebraically by changing one or both sides. It's going to be the same technique, same as what we did up here. We're just not going to do the table. We're not going to do the graph. We're just going to do the algebra part. All right, and so if this side has parentheses and this side doesn't, I think what I'm going to do is I'm going to get rid of the parentheses and see if it's the same. You notice the right-hand side just gets recopied twice, and that's fine. It's just going along for the ride. But the rest of it over here, I'm going to make the left side look like the right side. And so I'm going to write it twice, and then when I FOIL it, I get this. This is using no formulas at all. If you wanted to, you could use the perfect square trinomial formula, like a would be x squared minus 2a. A would be x, b would be y, and we get a minus b squared, or x minus y squared. But look, the left side equals the right side, and that's how I've done this proof. This is an algebraic proof. I've made the left side look like the right side, and we're done. Yay, I've proved it. There's no solutions. The end result is I'm done. I've proved it. Like there's the answer isn't x, or the answer isn't y, or the answer isn't 3 or 5 or square root of 2i or whatever, square root of 2. The answer is I'm done. I've proved it. The left side looks like the right side. Here, I'm gonna use a formula. This is a plus b squared. So this is if a equals x and b equals 5. So therefore, this is a squared plus 2ab plus b squared. And yep, the left side just looks like the right side. So it is. So the original is also true. I've proven this statement algebraically. Here, I'm not gonna deal with this 4 yet. I'm gonna deal with this squared first. A is x, b is 7, and I'm going to use the perfect square trinomial formula. We get x squared minus 14x plus 49. Distribute the 4 last, and we get that the left side is actually equal to the right side here. So check, we're done. Yay! The answer is not a number like 5. The answer is I'm done. I've proven what I set out to prove. If we know that this is true, so this side is equal to this side. Let's do this one more time. Oh, I'm sorry. So we've got this 2x squared plus y squared equals all squared. There's so many exponents of 2 in here. It's dizzying. And so many parentheses. I think what we just got to do is get rid of, the overall strategy here is just get rid of all the parentheses, whatever it takes. So here, a is equal to 2x squared, b is equal to y squared. That means this is a squared plus 2ab plus b squared. Okay, so then if I distribute the 2 here, from 2 times 2 is 4. And that's this left side completely finished, no parentheses. Here, to get rid of the parentheses, I'm going to choose the same thing. A is equal to 2x squared and b is equal to y squared. I'm going to use the very similar formula. A minus b squared is going to be a squared minus 2ab plus b squared. And distributing the 2, we get minus 2 times 2 is minus 4. Over here, I don't need to use a formula. I can just distribute this exponent. Because there's only multiplication here and no addition or subtraction, I can distribute the 2 here. 2 squared is 4, x squared is x squared, y times itself is y squared. And so therefore, next I'm going to distribute the 2 that came along for the right, and I get 2 times 4 is 8. So 8x squared plus y squared. I'm not going to write it out again, but this minus 4x squared y squared and plus 8x squared y squared gives you positive 4x squared y squared. These two terms cancel, and we're left with what looks like to be the same thing on both sides. So check, we're done. The left side equals the right side. I have proven that this original statement is true algebraically. We're going to prove the formulas. So, we're going to simplify by multiplying and removing the parentheses. So here, this is the difference of square formulas. What do? We got to get rid of the parentheses by foiling. And when we do that, when we foil, here's the f term. A times a is a squared. The outside term, a times minus b, is minus ab. The inside term is ab, and the last two terms are minus b squared. These two cancel, so we're actually left with a squared minus b squared does in fact equal a squared minus b squared. We've been using this formula for a while, and now we've actually proven that it will always work. We've trusted it before, but now we've proven it. Here, let's prove this formula. I kind of alluded to this before, but now let's actually do it. The technique is going to be remove parentheses, so get rid of the parentheses and make sure that the left side looks like the right side. How do we multiply these two together? Box method. So you can see a squared minus ab plus b squared is going to be written on the top, and a plus b is going to be written on the left-hand side. That choice actually doesn't matter. It's a 2 by 3, but you could write it as a 3 by 2, and you would still get the same result. So here, a times a squared is a cubed. B times a squared is a squared b. B times minus ab is going to be minus ab squared. Minus ab times a is going to be minus a squared b. And then this here, a times b squared is ab squared, and b times b squared is b cubed. The red terms cancel. The b terms cancel. I know that because they have the same exponents. They're like terms, and this is positive and this is negative. So the red terms cancel, the b terms cancel, the blue terms cancel. We're just left with a cubed plus b cubed. So removing the parentheses makes these both left-hand side true, so therefore we've proven the formula. All right, we're going to do the same thing here. We're going to prove that this side is actually equal to this side. Technique, remove the parentheses. So I think what I want to do is I'm going to you could multiply this middle term times this second term, this last term first if you wanted to, but you could FOIL it. But I think I'm going to FOIL the first two because I see this would turn into a difference of squares. P minus q, p plus q. Middle terms are going to cancel out. And it's just p squared minus q squared. Oh, and then look at this. The same thing is going to happen again. We've got the same thing. We've got a minus b times a plus b. So the middle terms are going to cancel out and turn into a difference of squares again. P to the fourth minus q to the fourth does in fact equal p to the fourth minus q to the fourth. So the left side equals the right side. Check, we're done. We've proven it. Here's a formula for you. Holy smokes, to the fifth power? Good night. Here's a formula, and I'm not gonna tell you where it came from, but the exercise here is just to prove that it's actually true. Technique, remove the parentheses. So let's write, what we've got to do is actually FOIL this all out. And when I say FOIL, I mean like FOIL with like a 2 by 5 box. We write a here and minus b here, and then the giant term, 1, 2, 3, 4, 5 terms all at the top. And then we multiply one at a time. I mean, that's the great thing about the box method. It keeps you organized. A times a to the fourth is a to the fifth. Negative b times a to the fourth is negative a fourth b. Oh, another way to stay organized, make sure you're always writing it in alphabetical order so that you can much more easily spot the terms that cancel later on. A times a third b is a to the fourth b. Negative b times a to the third b is negative a to the third b squared. Then here we've got a squared times a b squared. This is a cubed b squared. Negative b times a squared b squared is going to give you negative a squared b cubed. A times this gives you a squared b cubed. Negative b times this gives you negative a b to the fourth. I'm running out of colors. B to the fourth times negative b. B to the fourth times a is a to the fourth. A b to the fourth. B to the fourth times negative b is b to the fifth. And so you can see on the diagonals, all of these cancel out. Kind of similar to the previous one, except it's just way longer and there's more things to cancel. But the only thing left is going to be a to the fifth plus b to the fifth. So, pause. So you can see we've got a to the fifth minus b to the, that should be fifth. All right, b to the fifth equals a to the fifth minus b to the fifth. Yes, the left side equals the right side after we remove the parentheses, and so we're done. All right, each of these is an identity. It's an equation that is true for all values of x, or y, or a and b, or whatever the variable is. Here's some more identities just to review. Like this is an identity. You can see, does 3x equal 2x plus x? Yeah, the technique is to combine like terms, but you just get 3x is equal to 3x. You combine like terms, you get x plus 1 is equal to x plus 1. But here's not an identity. 3x minus 4 is equal to 5. That you can't get the left side to equal to the right side. There's not an infinite number of solutions. There's only one solution, and you can solve it. We're good at solving those things. Here, this has two solutions. These are not an identity. And this is not an identity either, because if you try and subtract x from both sides, you get 0 equals 1. There's actually no solutions. So no solution, two solutions, one solution. But if it has an infinite number of solutions, it's an equation that's true for all values of x, then it's an identity. So I'm not gonna do this, but I will say that you've got to do a lot of foiling and box method to, like, you'd have to square this, and then once you get the result of this, you multiply by this in a giant 3x4 box and do the terms. And then here you can use your formula. This is a sum of, like, you could turn this x plus 1 cubed. We've got a formula that helps handle this, or not. You'd have to, like, multiply x plus 1 times x plus 1, and then multiply the result times x plus 1, and then so you get like a 4 terms, and then you'd have to multiply those 4 terms by these 3 terms. You get a 3x4 box, and once you do all of that, combining like terms and box method, you'd be able to see that the left side does equal the right side. I'm not going to do that today in the video, but it's that's how you would do it if you were asked to do it. Here, this is lifted straight off the SAT prep. If the equation is true for all values of x, that is, if it's an identity, what is the value of b? Technique is going to be the same. Although you might be like, wait a minute, Berg, there's a b here. What am I supposed to do with the b? Well, that's what the SATs or the College Board is trying to see if you can do. If you can move forward, even though there's a letter where you expect there to be a number, if you can, like, access the stuff that I've taught you and other teachers have taught you and move forward with those techniques, even though there's a letter there instead of a number, then that's golden. So the technique is going to be the same. We're going to remove the parentheses, and we're going to use box method. X squared plus bx minus 2. I don't care that it's a letter. Just going to do what Bergman taught me how to do. And then times x plus 3 over here. When you do that, you get this curious thing that you actually can't combine. We expect that we'd be able to combine these, but we can't because there's a b. So we'd expect that when you add this 3x squared plus bx squared, we'd actually get 6x squared. We know that we're given that the equation is true for all values of x. This is supposed to be an identity. We have to choose the value of b that would actually make this an identity. So this plus this would have to be equal to this. So if that's true, then the 3 plus the b would have to equal 6. 3 plus b equals 6. Similarly, over here, we'd get 3bx and then minus 2x. And if this were an identity, which we know it is, we'd be able to combine these two together and get the 7x. So therefore, 3b minus 2 should equal 7. It doesn't matter which one of these we choose, we're going to get the fact that b is equal to 3. They both solve to b equals 3. So that's teaching you it's like how you do this using identities. There is an alternate method from the SATs, and this has nothing to do with a regular lesson, but you can actually let x equal 1 or any other easy value. Like 0 would have been an easier value, but then if you 0 times, like if this were 0, then b times 0, the b would actually drop out. So we can't choose the easiest value of 0. Let's just choose 1. I'm going to put 1 in for the entire equation because not like if I were going to say that it's true for all values of x, then it doesn't matter what value of x we choose. It should work as a solution. So x equals 1. You could have chosen x equals 10 or x equals 1,000. And you actually substitute it in and see what you get. So it used to be x squared, and now it's 1 squared. Bx, that's b times 1, minus 2 minus 2. X plus 3, 1 plus 3 equals. I'm substituting x equals 1 into the entire thing, both the left and the right-hand side. And now we've got an equation that's just equal to, that just has only one variable left in it. If you solve the whole thing, simplify it all down, eventually you get b minus 1 is equal to 4. B minus 1 times 4 is equal to 8. You can divide both sides by 4 and get b minus 1 is equal to 2, and then you can solve the rest. So that's that. Thanks for paying attention, and I'll see you in class. Oh, wait a minute. I wanted to tell you what my favorite holiday meal is. Favorite holiday meal is definitely Passover. It's a dinner that tells a story, a beautiful story, and a rescue story, and a story of Exodus, and it's just amazing. So that's my favorite holiday dinner. I want to hear what your favorite holiday dinner is. Is it Thanksgiving? Is it Christmas? Is it Passover? Is it New Year's? Do you have a different one? Tell me. I'd love to hear it.